Pluto, once considered part of our planetary system, remains a distant and perplexing celestial body. Recent statements from prominent astrophysicists like Neil deGrasse Tyson and Michio Kaku have thrust Pluto back into the scientific spotlight, suggesting a surprising new theory: this frigid world could potentially collide with Neptune. This raises several critical questions. How could such a collision occur, and what would be the consequences of such a monumental event? Is this just an intriguing yet improbable theory, or is there a deeper, more significant impact in store? Join us as we explore the possible effects of a Pluto-Neptune collision. Pluto, formerly classified as a planet but later reclassified as a dwarf planet, continues to intrigue the scientific community. Its peculiar orbit makes it an ongoing subject of study. According to recent findings from leading experts, Pluto's orbit comes alarmingly close to that of Neptune, prompting concerns about a potential disaster. But how likely is it that such a collision could happen? Pluto's journey around the Sun is distinct from that of other planets. It takes a long 248 years to complete a single orbit. This means that since its discovery in 1930, Pluto hasn't yet finished one full orbit. But Pluto's eccentric orbit doesn't end there. Its path is markedly different from the almost circular orbits of the major planets, and it is tilted at an angle of 17 degrees relative to the plane of the solar system. Pluto's path follows a significantly steeper trajectory than the other planets. A particularly fascinating aspect of Pluto's orbit is its periodic intersection with Neptune's orbit. For about 20 years during each orbit, Pluto comes closer to the Sun than Neptune, a surprising phenomenon given their positions in the solar system. This naturally leads to the question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influence of other planets. When Pluto's orbit was first analyzed, astronomers were perplexed by its unusual characteristics. Unlike the orbits of other planets, which mostly lie close to the ecliptic plane, Pluto's orbit was notably tilted and curved. This raised additional questions when astronomers realized that Pluto's orbit crosses that of Neptune. The study of this phenomenon highlights the complexity of space dynamics, especially when multiple celestial bodies influence each other's movement. The three-body problem in space describes the challenge of determining how three celestial bodies, like Pluto, Neptune, and the Sun, interact through their gravitational forces. Pluto's orbit is particularly chaotic. Even the smallest changes in initial conditions could lead to drastic shifts over time. However, these same irregularities have been found to stabilize over long periods. Simulations have provided more clarity on how planets like Neptune, Jupiter, and Saturn keep Pluto's orbit in check, ensuring stability over billions of years. Without the gravitational forces of these larger planets, our solar system would be far more chaotic. Pluto's orbit offers a textbook example of both stability and disorder in celestial mechanics. While its path is irregular, it has remained surprisingly stable over time, thanks to the gravitational forces of neighboring planets, especially Neptune. Predicting future celestial events, particularly with unstable orbits like Pluto's, is incredibly difficult. The inherent unpredictability of such systems makes long-term forecasts uncertain. While computer simulations have advanced our ability to model the behavior of planets and other celestial bodies, they also reveal the limits of our predictive power. This leads us to the question: why are respected astrophysicists like Neil deGrasse Tyson and Michio Kaku only now warning us about a potential Pluto-Neptune collision? Despite various stabilizing forces, they have expressed serious concerns about the possibility of Pluto colliding with Neptune. Such an event would undoubtedly be catastrophic. The collision would release an enormous amount of energy, most likely destroying Pluto due to its smaller size and icy composition. The debris from the impact could scatter across the solar system, possibly posing a risk to other planets and their moons. For Neptune, the collision could alter its atmosphere and even affect its orbit, depending on the severity of the crash. Michio Kaku, an expert in theoretical physics, brings a unique perspective to this discussion. His work in string theory and his broader views on space exploration help us understand the deeper connections between celestial mechanics and theoretical physics. Understanding the gravitational interactions and orbital dynamics of bodies like Pluto is crucial for planning future space missions. Such knowledge not only aids in exploring the outer planets but also helps predict and mitigate potential dangers in the solar system. The implications of a Pluto-Neptune collision go beyond just the destruction of two celestial bodies. The event could provide valuable insights into the physics of extreme energy and gravity. The collision might create conditions where predictions from string theory become observable. String theory, which posits that fundamental particles are one-dimensional strings rather than point-like objects, could potentially offer explanations for such high-energy phenomena. This collision might shed light on how fundamental forces and particles behave under extreme conditions. While the actual impact on Earth would be minimal due to our distance from the outer reaches of the solar system, the scientific consequences could be groundbreaking. The event would offer a rare observational opportunity to test key concepts of string theory and other areas of physics. Pluto's unusual orbit, with its distinct characteristics, continues to fascinate scientists, providing a glimpse into the intricacies of celestial dynamics. The reclassification of Pluto as a dwarf planet sparked considerable debate, but recent revelations about its orbit have reignited interest in its role in the solar system. Tyson and Kaku have both raised alarms about the potential risks posed by a collision between Pluto and Neptune, emphasizing the delicate balance of forces at play. Pluto's path, with its steep inclination and eccentric orbit, defies conventional understanding of planetary motion. Unlike the near-circular orbits of its planetary neighbors, Pluto's orbit crosses Neptune's, complicating predictions about future interactions. The role of gravitational forces from other planets, particularly Neptune, is crucial in maintaining Pluto's orbit despite its chaotic nature. The stability of Pluto's orbit has been preserved over long time scales due to the gravitational influence of Neptune and other larger planets. Mathematical models and simulations play a critical role in forecasting the movement of celestial bodies, helping us understand the complex gravitational interactions between planets. Although Pluto's orbit is unstable over centuries, it remains relatively steady within the larger context of the solar system's gravitational framework. The possibility of a collision between Pluto and Neptune, while speculative and unlikely in the near future, highlights the unpredictability of celestial dynamics. The warning from experts like Tyson and Kaku serves as a reminder of the constant flux in our solar system. While such a collision remains improbable, it underscores the complex balance of forces governing the movement of celestial bodies.